we're covering more material. All right. I was feeling we were getting ahead, and now I'm not sure whether we're ahead or not. I think we need to get moving again. So the next topic is this one right here, is building a priority queue. All right. And what's a priority queue is when objects arrive, they have a priority. And when you ask for an object, then it gives you the one with the highest priority, right? And we've sort of seen this table already, that just having a list that's sorted or unsorted isn't really a good method, right? We looked at binary search trees, right? You can insert, I mean, so quite frankly, you could use a binary search tree for a priority queue, right? An object comes with a priority, you insert it into the tree according to its priority, right? And then you want to find the biggest thing, you want to delete the thing with the biggest priority, right? So you could do that all in log n time with the binary search tree, right? But heaps are all in an array, and they're still log n, and I guess they're faster because they're all quicker and moving things around in an array. All right, so when I think, how do you implement a priority queue, right? I took this course a billion years before you were born, and we used heaps. All right, so that's what we're doing now. All right, so a heap is a tree like this, the binary tree, and it's going to have two properties. First, it's completely balanced. You see, not only is every node at the same height, every leaf is at the same height or one off, but it's about as full as it can be, right? And this bottom layer is filled in like this, right? And why is that? Well, quite frankly, we're not going to store it with pointers. We're going to store it in an array. And there'll be a nice mapping between where it is in the tree and where it goes in the array. In fact, it's the obvious mapping, right? If you're indexing from 0, then you just count them 0, 1, 2, 3, 4, 5, 6, 7, 8, right? So it's really, I tell you it's a binary tree, but the reality is it's stored in an array, right? And then for each node, it's bigger than all of its children. All right? So you'll see the 8's bigger than all of its children. 5 is bigger than all of its children. 6 is bigger than all of its children. Right? So there's no left to right concept at all. Right? Is it on the left or is it on the right? It doesn't matter. Right? Quick question. Who's at the root? The biggest, right? Right. So where does the biggest go? The biggest has to be the root because it has to be bigger than all of its children. But on the other hand, where can 1 go? Well, it's the smallest. It's got to be one of the leaves, but it doesn't matter which one, right? So when people say heap, they should really say, is it a max heap or a min heap? Because they're different. A max heap is putting the max at the top, and a min heap is putting the minimum at the top. And it depends on which one you want, right? Depends on whether the highest priority thing is the biggest number or the highest priority is the smallest number, right? And so now you can see 8 can be one of those two, right? All right. So So you should know how to map between the tree and the index. And here I'm indexing 0, 1, 2, 3 up to 9. And there are two reasons for doing that. The one is I do tend to index my arrays from 1. And I know, and I probably made these slides before Java was doing it, and also the math is a little easier, right? But here's a homework assignment, if you want one, is redo this math when you're indexing from 0. It's about the same, all right? So what are we saying? Here I'm indexing from 1, so 1 is at the root, right? And then you want to say, who are your parents? So if you take any node, say 3, who are your parents? Well, you multiply by 2, or you multiply by 2 and add 1, right? You can see for any node, 4 times 2 is 8, times 2 plus 1 is 9, right? So I think that if we index from 0, you would have to, the math wouldn't be quite as nice, right? And then similarly, you could say for any node, who's your child, who's your parent, right? And you divide by 2 and round down, right? So 5 divided by 2 is 2, and it's my parent, right? And then the last number stored is stored at n, right? Right. So 1, 2, 3 up to 9. I mean, it's not the biggest of this. I mean, just saying the index, the last one stored is at 9, right? And so now you want to say, hey, who's my child? Do I have a child, or is my child an empty pointer, right? Well, if I ask, I'm I, who's my child, and it's 2i plus 1, then I ask, if 2i plus 1 is bigger than n, then it's not a child, right? It's an empty pointer, right? Everybody see that? So, when we were doing pointers, binary trees using pointers, what did we have to know? We have to know, given somebody, how do you find their parent and their child? And how do you know if you have a child, right? And we're able to do all of those things, right? The only disadvantage of this over pointers is this is perfectly balanced, right? If you inserted something, there's no wiggle room to move it around, right? Everybody good with this? So, and then if you're trying to, if you want to learn this, in some ways you don't have to learn it. You just number them and think, who's my child, right? And you can see it feels like you're doubling, right? Because as you go down in the tree, there are twice as many nodes around, right? So the math more or less works, and you check it out, and it works, right? All right. So there are various things that we're going to do, and the one is you're given, right? You're given a bunch of numbers in an array. You suddenly pretend that it's in a tree, and we want to rearrange the numbers to make it into a heap. All right? Remember what a heap is. Every node is bigger than all of its children. Now, to sort the numbers takes n log n time, right? But we're not completely sorting them, right? Now, it's going to take you at least n time because you got to look at the numbers, right? But it doesn't take n log n time, right? We can do it in order n time. All right? Everybody understand what the problem is? All right. So, we're all about recursion, and recursion is you have friends, and you can give any problem to your friends that's smaller and meets the precondition, right? And then by magic, they're going to give you their answer, right? Without micromanaging them. So when we were doing recursive answers, problems on trees before, I have a question about my tree. What do I give my friends? The subtree, the left and right subtree, right? So I give these to my friends, and what do? They make each of them into a heap, right? Everybody good with that? And then nobody's looked at the root yet. So now we have a new routine we call not make heap, but we're calling it heapify. And what does it do is the precondition is that the left subtrial is a heap and the right is a heap, but we don't know about the root, right? The root's a problem. And what do is we basically have to move the 5, put the 5 somewhere good, right? And it's kind of like merge sort in some ways, right? All right, so we look at this and we say, it's not a heap. One thing about heaps is the maximum has to be at the root, right? Now, anybody know where the maximum's going to be? Exactly, right? It's just like when we did merge sort. The left isn't sorted, but we know it's a heap, so its maximum's at the top. And the right one, its maximum's at the top. And so where's the maximum? It's going to be one of these 3, right? And so what are we going to do? We're going to look at those 3 and figure out which one's the maximum, right? And what do we do with the maximum? Well, we're going to swap, right? The 5's too small, so it's going to come down and the 9's going to go up, right? And now what do we have? Well, I'm going to say more globally, we know every node is happy in that everybody below it is smaller, or is smaller, except for the 5, right? The 5's still a problem. So what we do is we ask, okay, who's 5 upset with, right? I guess we compare these 3 numbers and decide who's biggest. And 6 is the biggest, so we swap, right? So this was when I wrote a book on the topic, and it was before PowerPoint. All right, so you got 5s at the top, you switch it with 9, right? And then you compare the 5 and the 6 and the 4 together, and the 6 is the biggest, right? So the 6 bubbles up and the 5 bubbles down, right? And then you compare the 5 to the 3. You can look at the 5 and the 3 and the 2, which is the biggest. 5 is the biggest, so it stays where it is, right? So I think about the 5, right? Its value's too small, so I say it bubbles down until it's happy where it is, right? You keep swapping it, and you don't know which path it's going to follow, right? It always goes towards the bigger one, and it keeps bubbling down until it's the biggest, right? Is everybody good with that? Right? So I was talking to Andy just today, and we were like, what's going to be on the exam? And he said, he knew I was upset. And he said, yeah, well, we only need at most 30% in common. And we started listing topics that were going to be on there, right? We're definitely going to have some sort of binary search tree question. We're going to have some sort of heaps question, some sort of, hash table function problem, right? Yeah, so I said the chances are we could have a lot of it common, right? He might have some sort of trace out Java code question, in which case I'll replace it with, hey, did you really get loop invariance and friends question, right? But otherwise, I think we're going to be okay. All right? Yeah. The next test is not my problem. It's a coding. Yeah. Yeah. Yeah, because now it's a heap. What we need is for every node, everybody below it smaller. There's no left to right concern, right? So 9's the biggest, right? 6, it doesn't matter who's there at 6, right? Because the guys over there aren't below it, right? 6 is bigger than its children, right? So we're not really sorting them, right? If we wanted to put them in a binary search tree, then they would be sorted and it would take in log n time, right? But we're not really sorting them. And so this only takes order n time. Right? Everybody good with that? Yeah? Right. So no. So as I kind of said, everybody's going to be having a heap question. And unless he has some really weird, he did heap some really weird way, it's going to be the same question. Right? I can't imagine his question on heaps is different than the question I had when I was your age on heaps. Heaps are just heaps. Right? And I can imagine asking sort of theory questions, prove to me the running time, right? And I've never put those on tests because students will get them wrong, right? What do I put on a test? The heap looks, and here's the numbers, turn it into, do questions. Everybody should be able to do questions. We are both going to be both submitting questions to each other and proving them. And don't remember her name. And the other person, yes. No, 3 of us. Right? There are 4 sections. Jackie is 2 of them. There are 3 professors. But I will, in fact, I didn't give them to you because I'm lazy. I do have the exam I gave from last year. And I'm willing to just give you that same exam and I wouldn't have to do any work. So, and I do know there's a question which is, here's a heap, do this to it, right? All right, so here, this is just what we're doing. Everybody get this? Right, and then you stop. Running time. All right, so we can analyze the running time either by it's a recursive program. All right, so this program is going to take log n, right? You can think of it iteratively. I'm following one path down the tree, so that's log n. Or you can think about it as a recursive program where I have one friend and you do they call it master-slave theorems or something. What master theorem? There's no slaves involved. Sorry, that was my bad. All right, and you get this, right? All right, so then how do you, don't say I never gave you code, right? How do you make, oh, here's just code for heapify, right? There's an iterative version, there's a recursive version. It's not very hard. You just bubble it down, all right? And then make heap, remember we recurse, and then you call heapify, right? So what's the running time there? Here's the recurrence relation, and log n, right? Log n is not n. It's closer to 1, and we haven't taught you how to solve this, but it boils down to order n, and then here's an iterative version of it, right? And an iterative version is you go backwards through the numbers, right? You first go, hey, these numbers, they're just one number, so clearly they're heaps, right? And then you go say, oh, what about 9? Is it a heap? And you say, yeah, you call heapify, and it's a heap, right? And then you say, what about that? Is it a heap? And, right, it's not, so you turn it into a heap. And you say, what about that guy? And you turn it into a heap. And then you say, what about that guy? And you turn it into a heap, right? So you hit the nodes bigger and bigger until you get to the top, right? Does that make sense? And the running time of that, well, it's a lot of math. It's a lot of math. And does anyone want to do the math? I don't think so, right? But you can kind of buy, well, that's, I guess each step, right? We do in steps, and each step takes log n. So you're thinking it's going to be n log n, right? But the log n wasn't really, for most of your guys, the tree, for half of them, the tree's only size 1 or 2, right? It's only the last guy that has size log n, right? So there's kind of a geometric sum to it instead of an arithmetic sum, and we lose the log n, right? But I'm never going to ask you that, right? And I'm sure Jackie won't. So everybody good? All right. So now, all right, so what's a priority queue? Remember, we have them stored there based on their priority. And who do we want? This is going to be a max heap. So the priority might be, the max might be on the top, right? And you know, I'm making max heaps. 30 years ago, I flipped a coin and made max heaps. If Jackie's teaching them, he might be teaching min heaps, right? So if on the test is a min heap instead of a max heap, get over it. You know what I mean? It just turns everything around, right? So, right? So there's, we say where is it? It's there, right? All right. So it's at the root, and we're popping it off the priority queue, so it's gone, right? And it leaves a hole. Leaves a hole at 1. Do we like holes? No, the universe abhors vacuums, right? Power structures. So that guy's gone. Now, if we want to keep this the right shape, who needs to move? Yeah, that you would think. You would think you move them up, right? But then in the end, the shape's going to be wrong. All right? So you're absolutely right, and we're going to do that. But right now, let's not worry about it being a heap. Let's worry about it being the right shape. And what do I mean by shape? Right? It's got to be filled up like an array. Right? Yeah. 9, right? See over here, who goes? Who goes? 9 has to go, right? So whoever's in 9, right? We move them up, right? We take 9 out and we put 9 up there, right? Everybody kind of buy that? And the reason we did that was to keep the right shape, right? Now we come back to you, right? Now there's a value at the root that's not a good value, right? And right, so here we had the value there, the value moved up, and then it's not a heap. Yeah, but the left child and the right child are heaps, right? And we know how to call heapify, and it bubbles, and the bubble, the 3 bubbles down and finds the spot, right? Now, if we did it, what you did originally, the 3 would have bubbled down with, there would have been a blank there, and you would have bubbled the blank down, and the blank would have ended up in an arbitrary place. And we don't want a blank in an arbitrary place, right? So that's why we put the 3 up and bubble the 3 down. Right? Everybody good? Yeah. Yeah, so that's why I drew both pictures. Yeah. Uh, yeah, here, what are we doing? The three is there. And we put the 3 up there. No, we just put it temporarily there. We put it there. It's not the biggest number, right? Something like 21 was the biggest, and the next biggest is probably 20. 3 is some little number. It doesn't belong there, right? But we made the shape right, right? And now what do? We say, now we compare 3, right? The 3 in the triangle, and the 3 bubbles down and fall somewhere. Yeah? Yeah. No. Heaps, truth. The truth is heaps aren't trees at all. They're arrays. And that's why they're faster, is because you're not doing all this, All right. So one of our rules is we have 2 rules. The one rule is that for every node, the children have to be smaller. The other rule is that the tree has to be completely balanced. And in fact, the last, right, we've never talked about things at a given height being a row or something, right? But all the rows are filled until the last row, and then the last row is filled in order, right? That's a requirement. Are you following? Right? So when we delete the top node, it's no longer the right shape. So to keep it the right shape, we take who's ever in 9, which might be a 3, and we move it up. Right? Is that answering your question? The purpose is to keep the right shape. Right? Oh, so here we're doing it again, right? It bubbles down. You compare these 3, and the max moves up, right? And then we compare these 3, and the max moves up. And then at some point you stop, right? Yeah. Yeah. So you're given it. Remember, we called make heap. You're given an array, random, arbitrary, and you think about it as a tree in the right shape. And then you either recursively or iteratively make the whole thing into a heap. All right, so a recursive algorithm is you recursively make your left subtree and your right subtree heaps. And then it's all heaps except the top, and the top bubbles down, right? So that's one algorithm. The other algorithm was 8, 7, 6, 5, and 5 are clearly heaps, right? So then you make 4 into a heap. And then you go over to 3 and you say 3's left child and right child are heaps. So you bubble from 3 down and make it a heap, right? And then you go over to 2. 2's left child is a heap. His right subtree is a heap. So you bubble the 2 down and you get it a heap, and then you do the top. Those are the 2 algorithms, right? Does that make sense? And not only, I think that they might even be the same algorithm. You're going to come up with the same answer, right? Just different ways of thinking about it. All right. All right. So now what are we doing? Somebody comes along and inserts somebody into the heap, right? They want to say, hey, I want to put 21 in. New guy arrives. So where do you put him? Again, to keep the shape, you put him there. But now he might be too big, right? So So now what I do is you bubble him up, right? Now you don't have to compare him to the 8, but you compare him to the guy up there. And if the guy up there is bigger, right, then you swap. And right. In fact, here I panicked for a minute, but if 21 is bigger than this guy, we're swapping, and this one we know it's already heaped, so this one's bigger than this one, then it follows that the 21's bigger than this guy, in which case it's okay to move them up, right? I just did a little proof there on the fly. Everybody get that? So we don't have to look at the guy at 8, right? We compare the guy at 4 and the guy at 9, and we bubble the bigger one up, right? And then we compare the 20 to the guy in the 2, and we bubble the biggest one up, right? And then you compare these, and oh, it's a 30, so we stop, right? Does that make sense? So there's this idea to bubble down, you look at 3 things, and it helps you choose which way to go. And if you're bubbling up, you just look at your parent, right? And you keep swapping as long as it's not in the right place, right? And so that takes log n time, right? All right, so these slides I teach in the 3101 class because we use heaps at some point, right? So what are we doing here, right? This box over here with the heap, oops, that was squeak, is a data structure that we're accessing, right? And remember, we had the idea of a position. So the outside world, if let's say we're doing some algorithm where I have some object C, and I know it has priority 21, right? And I want to, one thing I know about it is I store a pointer into where it is in the tree, right? Does that make sense? Because I want to, the tree is for every object C, I know where it is in the heap, right? Now, why am I doing that? Because the outside user, right? This is called an adaptable heap. I want to change the priorities, right? I'm the outside user. Quite frankly, I'm doing Dijkstra's algorithm to find the shortest path, but you don't need to know that, right? I know that the value of C changed from 21 to 39. It got better, right? So I'm going to follow this pointer in and change the 29 to, let's change the 21 to a 39, right? Everybody buy that? Now, when I do that, what's the problem? Is it still a heap? No, it's not a heap anymore, right? But everything's a heap except that guy, right? And we know what to do with that guy. What do we do with him? We bubble it up, right? If we made him worse, we could bubble him down. If we made him better, we bubble him up, right? So that's exactly what we do. Well, now the outside world, it's not his job to do it, right? Inside, its job, right? So inside says it's not a heap, so we bubble him up, right? We compare him to the guy above, and the 30, it used to be right, but now the 39 goes up, right? And now remember what I'm big on is loop invariants, and one type of loop invariant are these system invariants, right? So one of our system invariants is that the outside world, C, is pointing at the guy who has the value, you know, it's representing C. So when we moved the 39 up, we have to tell the outside world to update its value. Right? Everybody get that? All right, that's good. But who did we move down? Right? We moved down to 27. And there's somebody in the outside world cares about 27. Right? Mr. F cares about the 27. And what's our loop invariant? Is that the 27, the F guy is pointing at the 27. Why is he pointing at it? In case he wants to change it. But is he pointing at it now? No, he's not pointing at it because we moved it. So how do we get F to change? Right? You could say, well, you could say F change, right? You could do that. Yeah, but I'm on the inside. I don't know who F is, right? You see what I'm saying? So all these, we got 3 different people, right? We got the guy handling the heap, we got the guy handling C, and we got the guy handling F. And they might not even know each other, right? So C has a pointer in and goes in and says, I'm changing, right? Let's do it again here. The C comes in and says, I'm changing that to a 39. And then the heap says, all right, that's good, that's good. I'm going to compare and I'm going to swap them. And I'm in communication. The heap says, I'm in communication with Mr. C, right? Mr. C, you got to move, right? Now, what about Mr. F? I'm Mr. Heap, and I don't even know. I haven't even met Mr. F, right? I know Mr. F's out there somewhere, but I don't know who he is, right? So what do we need? We need an address of Mr. F, right? We need to find Mr. F. And where are we going to store Mr. F's address? Well, not the C. Who's going to hold Mr. F's address? Yeah, exactly. This 27 is going to hold it, right? The heap must be able to talk to the outside world, all right? So if we go back here, 27 has a pointer to F, right? And when we swap them, what comes down is not only the 27, but the pointer to F. And then we can go out, right? Here we can go out to F and say, hey, F, I moved. And then F can update its pointer, right? Does that make sense? And so you need all those pointers, and you do it all in log n time. Yeah? I wasn't as worried about C because C started the conversation with me.
That's like one direction pointer. If we didn't have also the C's position.
Yeah, for sure. Yeah. I mean, so that's what I have here is the loop invariant is that for every object, there's a pointer in and a pointer out. And we have to maintain those. And when C started the conversation saying I'm changed the value, so it goes out, and then, yeah. You want to do the whole animation again? The switch. All right, so here, C says I'm changing, right? And you know that there's a pointer from C to 21, and there's a pointer from 21 back to C, right? And then you say, oh, I compare to the root. Now there's a pointer from the 21. There's a pointer from 27 to F, and a pointer from F back to 27. So then we swap them, right? And we swap not only not only those values, but those outer pointers, right? So then we can from the 27, we can go out to F and then tell F to go back to point to the new location of 27. Right? Does that make sense? And so as we bubble up, we might have to move up a distance of log n. As you go up, you correct each one. Yeah. Yeah. You have to, for each new one, you have to come out and say, hey, F, I've moved. Yeah. Yeah. Everybody get that? Well, not the 2. The pointer from 27 to F doesn't change. Well, it comes down, right? Yeah. Yeah. The 27 had been up there, and the 27 moved down. And when the 27 moved down, the pointer to F came with it. And then we go out to F, and we update the pointer from F back to the heap. Right? Everybody get that? Yeah. Yeah. And then when F is trying to update its priority, it would go in and, oh, the priority is not what I think it is. It's gonna be upset. Right? Yeah. Yeah. And I like to think about it is you tell me what your invariants are, and you need to maintain them, right? Why do we need a pointer from C in? So that Mr. C can go in and change the priority. Why do you need pointers out? So we can tell Mrs. F to move. Right? Does that make sense?
Isn't it because you define the system invariant in this case to be that that someone who's an outsider knows about the data item and location?
Yeah, and the data too. Everybody outside knows where they are, and everybody inside knows who's talking to them. Right? There's a pointer in both directions. Right? And this all happened. Oh, that was the. Yep, that was the don't work any more button. All right, so here's kind of the picture, right? Right. So in this picture, the gray is the heap actually stored in an array, and you see the outside world is pointing in and out. Right? Does that make sense? Everybody good with that? So I can definitely imagine, we give you, here would be a great question on an exam, right? This is, I think, as hard as it's going to get. I draw you this picture. I say, Mr. E is updating the 5, either increasing it or decreasing it, right? And what do you have to do? You have to go in and bubble it up or down. And as you bubble up and down, you have to make sure that you have to redraw all the pointers, right? Not so hard. You could do that, yeah? You guys really follow me around, don't you? I lose track of who's in what course, but many of you are in both of them. Yes.
Hello. I see I'm still unaudible.
Yeah. Yeah. I haven't thought about all of that, but absolutely. If you take in the bottom and there's pointers in and out, and you move them to the top, then you have to adjust the inner outer pointers, right? In fact, she just came up with a better exam question, right? I give you this picture, and then I tell you I'm deleting the root, right? And what do you have to do? You have to take who's kind of bottom left is C, right? You have to move C to the top, and then you have to bubble C back down again until it's a heap. And then you got to remember who's moved and update all the pointers, right? Everybody, in fact, if I was doing it, I would first do the heap, and then I would just say, okay, who's pointing at who? And I quickly fixed the pointers. And from a god on the outside, it's easier than an algorithm, right? Yeah. Yeah.
Expect us to draw every single step, or can we skip like?
I would say it would be, this is the picture now, and then you give me a new picture of it when it's done, right? And then what would the marker do? Marker would check, bang, there's a fixed tree that needs to be there, right? There's only one way to bubble it up, right? And then they would check, did you correct all the pointers, right?
Say like don't have to draw the very bottom going to the top. That's one picture.
No, I'm not, if I was going to do, I also want, another thing is when I make the test, I want to make it easier for the marker, right? So one picture. And one thing I'll tell you right now is if you're ever doing a question and you think, oh, there are two ways to do this, I could get two different answers. It's not my question because I make every question so there's only one answer, so it's easier for the marker, right? So that's a little hint to know what is the one thing I'm supposed to do, right? Does that make everybody good? All right. All right, so selection sort. Everybody remember selection sort? The loop invariant is we've sorted some over here, and the rest are over here. And maybe we haven't actually covered this. All right. Everything over here is smaller than everybody over there, right? Smaller or equal to. And then what I do is I find the biggest number. These aren't sorted, right? So I find the biggest number that's over there is the 4, and I put it where it belongs, right? Everybody right? Insertion sort is just, these ones are sorted, I don't know which one. I take anybody and insert them, right? Selection sort is I take the biggest guy that's unsorted and put them where they belong. Or I take the smallest guy and put them where they belong, right? Everybody buy that? And this takes in log in time because I had to go in here and I got to find the biggest, right? And that takes me order in time, and then I put it where it belongs, right? So that's in squared time, right? In squared time. In times I have to go in, right? Yeah, but what happens if we're doing heap sort, right? What's heap sort? All right. So this is a nice fast heap sort. You put everybody in the array, right? Now we got a loop invariant. The loop invariant is there's some line here where these guys are sorted, right? And these guys are not sorted, right? But what are these guys? Are they in an arbitrary order? No, they're a heap, right? And how are they stored? Well, this is a little array. They're actually in this array, but we think about them as being in a tree. That's a heap, right? So these guys are actually in the array where they belong. And these guys we think about them being in this tree, right? And then what do? Is we take the maximum, which is at the root, it's here, and we put it where it belongs. Where does it belong? Well, this was our line, right? So here's a little fun thing, right? This is a heap. So when we delete the maximum, what happens? The 5 is the last guy in the heap, right? So it's removed. Boop. And it's put up here and bubbles where it belongs, right? And we remove the maximum. Conveniently, where does the maximum go? Ooh, it goes here. Why? Not because it's part of the tree, but the tree got smaller. It now belongs where it belongs, which is here. Right? Does that make sense? So it's actually a pretty nice algorithm. Right? Yeah.
Place going to that spot, or it can also be inserted in somewhere in the middle in the.
No, it always goes there. Right? Why does it always go there? It's because our loop invariant, let's restate our loop invariant. Because I might have gotten it wrong. The loop invariant is these guys are sorted and actually where they're supposed to be in the array. These guys, they're not completely undersorted. They're a heap. And everybody here is less than or equal to everybody here. So when we take the 5, where does he go? He goes right there next to the 6. Right? Everybody's smaller. So the maximum is going to go right where it is. Right? Does that make sense? Right? And so it's quite fun that this number comes out because we're making, it's the last in the heap. So we want to keep the shape right. To keep the shape right, we got rid of that. And he goes in there, but the max comes out of there and goes there, right? It's pretty nice. You swap these two, and then this one bubbles. Everybody got that? And that is called heap sort. Oh, here I'm saying it again, right? These guys here are where they belong. Those guys there are in a heap, right? This part is an array. That part is a heap, right? And here it is again. And then the 5, well, we delete the 5. Where does the 5 go? Right? The 5, we swap the 2 and the 5 because we're deleting the 5. So the 2 goes up where the 5 is, right? And then we maintain the loop invariant. The 5 has to bubble down again. Let's see, the 2, right? Then the 2's at the top. So the 2 bubbles down to here, right? And where does that 5 go? Well, luckily we have a spot for it, right? Hoping everybody's saying, hey, actually that was pretty cool, right? Right? There's an algorithm for it. Here's heaps. Here's going through the heap. You can go, right? Right. So I guess here we're, I don't know. Do we need to do this? People good? You can go through this example when you're studying. Running time, right? Remember it took order n to turn into a heap, right? And then heapifying takes you log n time, and you got to do it for each, right? Each step, and so the total time is n log n, right? All right, everybody good? All right, there's another thing about trees that I love, and I don't think it's part of the course. And so if we have extra time, we'll cover it. Before I thought we were ahead, and now I'm not sure if we're ahead or not. So let's remember that this is useful if you ever want, we can come back to it and move on.